Cambridge International AS and A-Levels Chemistry Paper 2 ACE Level Structured Questions May June 2025 Paper 22 is what we're going to be doing today. Diamond and graphite are both crystalline solids made from carbon atoms. That's what we know. Graphite conducts electricity. Diamond does not conduct electricity. Name the type of lattice structure present in the crystalline solids diamond and graphite. Name the type of lattice structure. Giant molecular structure or giant covalent structure. Explain how graphite conducts electricity. There's no rocket science in it. Each graphite atom connected to 3 other graphite atoms by covalent bonds. So basically, you know that carbon has 4 electrons in its valence shell. So if this is a carbon atom, it's going to have 4 electrons, 1, 2, 3, and 4. And in graphite, out of those 4, 1, 2, and 3 electrons are involved in bonding. So the 4th unbonded delocalized electron can move through the layers of graphite to conduct electricity. So the main particle that's going to conduct is delocalized electrons can move through the layers of graphite. And you should know graphite is like hexagonal layers. It's a layered structure. Explain why diamond does not conduct electricity. Because in diamond, each carbon atom involves all its 4 valence electrons in bonding. So there's no delocalized free electron to move. It has no delocalized free electrons. So simple. Separate samples of PCl5, phosphorus chloride, or you can think about it as PCl3 as well, or silicon chloride, SiCl4, are each added to an excess of cold water. So what we're doing is we're simply hydrolyzing our chlorides. Write an equation for each reaction. So first, let's write for PCl5 plus water. So you should remember the first thing that we're going to form is H3PO4 plus HCl. Now 5 HCls and then 5, 6, 7, 8. So we're going to use 4 O2s and done. Balanced equation. Just had to add these 2 numbers to balance it out. So remember that you have to learn these equations. By the way, I've not learned it. I just simply know that you're going to add water to it, so you're going to form phosphoric acid, and then because you have chloride, so you're going to form like HCl thing. Well, that was simple for me. Then I have SiCl4. Now, I've not learned it, I'm telling you. I'm just like, I don't know. SiCl4, so first thing I'm going to form SiO2 plus HCl. And I'm going to form 4 HCls. And now 4 HCl, so we're going to put A2 here. Balanced? Balanced. Good to go. If someone tries to outsmart the examiner by writing the equation and not balancing, be clear of the fact that you're only going to get like 1 out of 2 marks. The second mark is for balancing. Describe the appearance of PCl5 and SiCl4 at room temperature. You should remember one thing, that phosphorus chloride, it's a solid, whereas SiCl4 is a liquid at room temperature. Okay, so it's a white solid, and this one right here is a liquid. I don't know the color of the liquid, I'll be honest, but I know it's a liquid. Silicon chloride is a liquid, but when they ask for appearance, we have to write the color and the state. So, well, you should learn the color. It's a colorless liquid. Colorless liquid. You have to learn it because, you know, they're not going to give you the marks. Whenever they say you have to describe the appearance, remember color and state. So I'm going to highlight this part because that's, I guess, a learning thing you got to do for like all the chlorides and whatever there is. Compare the appearance of the mixtures produced when each reaction is complete. Okay, so over here you know that we're producing HCl, and whenever we're producing HCl in any reaction, we see white steamy fumes of HCl. So to compare means you can write both the differences as well as similarities. So the first thing is going to be white steamy fumes seen for both reactions. And secondly, over here, you can see that we have one additional thing. We're forming SiO2. So with silicon chloride, we're going to see a white solid, okay? Because SiO2 is going to produce a white solid, but over here, we're going to form two aqueous solutions. You're going to see no solid. Some oxides are amphoteric. Amphoteric mean they react with both acids and bases to produce salt. In what example are zinc oxide, aluminum oxide, tin oxide, and whatnot. Describe what is meant by amphoteric. Reacts with both acids and bases to produce salt and water. That's an important line. Okay. They can behave as acids with bases and as bases with acids. Okay, they're going to react with both. Species behave as acids and bases. That's the marking scheme definition. So that's what I've written, and what marking scheme says is it's like similar, but the wording's a little different. Species, I'm going to write the marking scheme as well. It says species behaves as both acids and bases. And the second definition it says, or species reacts with both acids and bases. So that's what I have written. No worries. Identify the formula for period 3 oxide that's amphoteric. I just told you it's aluminum oxide that's amphoteric, and that's the formula for it. Al2O3. Just learn the formula for all period 3 oxide. Sodium oxide, magnesium. You don't need to learn the formulas. I guess that's elementary school science. Aluminum oxide, sodium, magnesium, aluminum, silicon, phosphorus, and then there's chlorine, but that's not, I guess, part of the syllabus, right? So simple. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, SO2, SO3, and then there's chlorine. Okay, the melting points of different oxides are shown in table 1.1. Complete table 1.1 by identifying the strongest force of attraction in each oxide. So we have to identify the strongest. There may be other present, but we only have to care about the strongest, right? That is broken during the melting. Okay, so we have to melt the substance and then realize we have instantaneous dipoles, we have permanent dipoles. H, that's hydrogen bonding. C, that's covalent bond. I, ionic bonding. So we have to complete the table by writing these words. So SO2. SO2. Okay, let's draw the structure of SO2 to understand what kind of force is going to be present. I guess that's a very gray area for you guys to realize the force without drawing the structure, because you cannot identify either dipoles or cancelling or not. Because I tell you one thing, okay? If you think that I'm talking like bullshit, then look, this is carbon and this is oxygen. Now, you might think carbon and oxygen have hell of electronegativity difference, and you are correct, it has. But you know the only force that's going to be broken while melting this is a polar bond. Carbon-oxygen bond is a polar bond. This is partial positive, this is partial negative. Despite being polar bond, despite having dipoles, you know what the force is going to be that's going to be broken when it's going to be melted? It's going to be instantaneous dipole. You know why? Because despite having polar bonds, the dipoles in carbon dioxide cancel out. Why do they cancel out? Because it is a 180-degree linear molecule. So there's a partial negative charge on this oxygen as well, and both of them pull the carbon towards itself equally. That's why the partial charges are there, but still don't contribute to the permanent dipole. Got it? So for SO2, you got to realize if it's a linear molecule, they're going to cancel out. But it's not. There's one oxygen here and one oxygen here, and we're not interested in the bonding, but we know that sulfur is in group 6. So 1, 2, it's not linear. It's going to pull down here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, It's gonna pull down here and it's gonna pull down here. So the bond angle is not 180 degrees. So it's gonna be a polar molecule, and when it's polar, we know the strongest type of bonding is gonna be permanent dipole. And second thing I wanna tell you guys, hydrogen bonding is only gonna be there when a hydrogen is bonded to nitrogen, fluorine, or oxygen. So over here for SO2, we're gonna break permanent dipoles. For H2O, though there are permanent dipoles, there are instantaneous dipoles, but still, because it's water, we have hydrogen bonding here, because in H2O you can see that one oxygen is bonded to hydrogen. And I just told you that if oxygen is bonded to hydrogen, oxygen or nitrogen or fluorine, then you're going to have hydrogen bonding. So H. SiO2, giant covalent structure, going to melt. You got to break the covalent bonds. There's going to be a C here. Na2O. I don't think it needs any explanation. If someone doesn't know this, I don't feel like... No, it's fine. Just sodium oxide. Sodium is going to be positive, oxygen is going to be negative. There's going to be ionic bonding between them. Magnesium oxide, again, there's going to be ionic bonding between them. Simple as it looks. A student suggests the following hypothesis. The stronger the covalent bond between atoms in non-metal oxides, the higher the melting point. Well, that doesn't make sense, because use table 1.1 to deduce if this hypothesis is true or false, or if there's not enough information to make a conclusion. There's not enough information at all, because we're not given the strength of the covalent bonds. You see, he's saying the stronger the covalent bond. If you're given with the bond energies, you can make a conclusion. But, well, there's not enough information because you're not given with the bond energies. So I'm going to say not enough information. The stronger the covalent bond between atoms in non-metal oxides. How many non-metal oxides do I have in my table? I have SO2, H2O, SiO2. The stronger the covalent bond. I'm not given with the strength of the covalent bonds. So not enough information. You got to realize one important thing. When you're melting SO2 and water, you're not actually breaking the covalent bond. You're breaking permanent dipoles here and hydrogen bonding here. Only for SiO2 you're breaking covalent bond. Whereas the hypothesis suggests the stronger the covalent bond between atoms in non-metal oxides, the higher the melting points. So you're going to tell no covalent bonds are not broken. So you're going to tell covalent bonds not broken in SO2 or H2O while you are melting them. That's a very clever question the examiner asked. He wanted to see you guys, whether you guys realize the fact that what kind of things are you breaking when you're melting a substance. Covalent bonds are not broken in this, but with SiO2, covalent bonds are broken because that's a giant covalent structure. The only thing you have is covalent bonds. You're going to break them. So over here, we say that covalent bonds are broken. Easy. A sample of iron contains 3 different isotopes and has a relative atomic mass of 55.8. Define relative atomic mass. It is the weighted average mass of all the isotopes of an element compared to unified atomic mass unit, or compared to 1/12 of a mass of a carbon-12 atom. That's a very simple definition that I learned. The weighted, and a lot of guys in the May June paper 22 messed up with this definition. The weighted average mass of all isotopes of an element compared to unified atomic mass. Or you can say compared to 1/12 of a mass of a carbon 12 atom. What is unified atomic mass? It is the mass of 1/12 of carbon 12. Table 2.1 shows the abundances of two isotopes present in the sample of iron. Use table 2.1 to calculate the relative isotopic mass of the third isotope of iron in the sample. Show you're working. Well, not difficult at all. What we're going to do is first subtract these two to find out the abundance of the first. Third 100 minus 91.9 and 6. 100 minus 91.9. Yeah. Minus 6. That's 2.1 for the third one. Equals to 55.8, and if you're going to solve it, the value of x is going to come out to be 56.9. Solve it. I don't think that's simple mathematics. You just have to solve for the value of x over here, and it's going to come out to be 56.9. Reduce the number of pairs of electrons in the 3D subshell of an iron 2 ion, which means iron 2 plus, which has lost 2 electrons. So what are we going to do? We're going to go to the product table. Where is iron? This is iron. Okay. If you look over here, 3D1, 3D2, 3D3, 3D4, 3D5, 3D6. So iron basically has, this is the d subshell of iron, which is going to have 5 orbitals, 1, 2, 3, 4 and 5. And it basically, I'm talking about iron. It has 6 electrons, 1, 2, 3, 4, 5 and 6. And now, okay, taking out 2 electrons from this, you know that whenever we take out electrons, we don't take out electrons from the d subshell first, we take it out from the S. So this is 4s and that's 3d. So if I have to take out 2 electrons, I'm not going to put my hand on the 3d one, I'm going to steal it from the 4s. So the 2 electrons are going to be taken out from the 4s. Nothing happens to the 3d part. So 3d is still going to have 1 pair of electrons. That's 1 pair. And these are the unpaired electrons. So in an iron 2 plus, the 3d subshell has a total of 1 pair of electrons, because in 2 plus iron atom, the electrons you're taking out, you're not taking them out from the d subshell, you're taking them out from the s subshell. So 1 pair. Hope that clears up things. Sketch the shape of the lowest energy orbital in the shell with the principal quantum number 2. The lowest energy orbital, it's going to be the 1s orbital, and the shape of the s orbital is a perfect sphere. So you just have to draw it something like this. Complete the number table 2.2 to show the information about the particles in one ion of Fe3+. 3 plus means number of particles present in one ion of 56. There are 26 protons here. So 56 minus 26 is 30. So 30 is the number of neutrons. And since it's 3 plus, that means it are 26 protons and 26 electrons. But since it lost 3 electrons, so 26 minus 3 is going to give me 23 electrons. Why minus 3? Because 3 plus means lost 3. The atomic radius of iron is this. Suggest the change to the radius of any after an iron atom reacts to produce iron 3 plus ion. Explain your answer. The radius decreases because electrons are lost. So now the nuclear charge, there's going to be greater effective nuclear charge in the remaining electrons. Simple. You know that for metals, the ionic radius is smaller than the atomic radius. So no matter what metal you are dealing with, the ionic radius is always going to be smaller because you're going to lose electrons anyhow. And when you lose electrons, you lose like a part of your atom. Define addition reaction when two or more reactants react to form a single product only. Addition reaction means that one product is going to be formed. That's the core definition that you should know. Two or more reactants react to form a single product or one product. Okay? Complete figure 3.1 to show the mechanism for the addition reaction between C3H6 and HBr to produce 2-bromopropane include charges, dipole, lone pairs of electrons or curly arrows as appropriate. First, there's going to be a partial positive charge on hydrogen, a partial negative charge on bromine. This nucleophile is going to attack this hydrogen, and then this bond is going to break heterolytically. Bromine is going to get the electrons, something like this. And once this fella happens, a major sacrifice. Done. So that is all you had to show the examiner. Just one thing, that this H could be drawn somewhere here. What happens is that first, because this pi bond and this sigma bond, whatever, because this bond in the alkali is a nucleophile, it has this electron density high, it attacks the partial positive hydrogen, which breaks this bond heterolytically, and hydrogen, which is partial positive, is now gonna be like left with nothing. It's gonna form H plus sign, which is gonna basically attach here. Why here? Because the negative part, according to Markovnikov's rule, is going to attach to the carbon that is less hydrogen. So it's going to attach to the, it's going to attach here. So that's why a secondary carbocation is going to be formed here. If you try to attach this hydrogen here and form a primary carbocation on this carbon, you're going to lose marks, because a primary carbocation, you know that it's not stable, it's unstable. So you are not going to form it. If you're going to form it, do it on your own risk. If you're going to test examiner's patience and see what happens if you make him angry, then well, do it. And this bromidine now is going to attack this carbon, which is like positive, and then it's going to get attached. So don't forget these things. Explain why the major product of this reaction is 2-bromopropane rather than 1-bromopropane. So you have to tell that the intermediate that's formed for 2-bromopropane is more stable than that's formed for 1-bromopropane because of the positive inductive effect of more alkyl groups. Because there are two alkyl groups for this carbon, right? Two alkyl groups, this CH3 and this CH3. So there's going to be a greater electron donating effect because the alkyl groups have a positive inductive effect. That's an electron donating effect. But if you form a carbocation here, you only have one alkyl group, so there's a less positive inductive effect. Explain why major product of this reaction is 2-bromopropane rather than 1-bromopropane. Done. H2 and nickel are added to alkene X, so you are adding hydrogen and then you're adding nickel. You know what kind of reaction is going to happen. It's going to convert into an alkene because there's going to be addition of hydrogen in it. And figure 3.2 shows how the concentration of X changes with time. So concentration of the alkene is decreasing because X is an alkene. Concentration of alkene is decreasing because obviously alkene is being converted into alkane because you're adding hydrogen to it. Use figure 3.2 to identify the limiting reactant in this reaction. Explain your answer. So you can see that after some time the amount of X has become constant, but it has not reached 0, so there is still some X left. So the limiting reactant is, I guess, going to be hydrogen because it's going to be used up. And the explanation is going to be that even after the reaction is over, the lines become flat and there is still X left. H2 is the, please someone, I wonder if someone writes nickel is the limiting reactant. No, it's the catalyst. It's going to be regenerated at the end of the reaction. It's not going to be used up. Catalyst is the best thing, bro. It speeds up your reaction, it makes it faster, and it's not even used up. Like in an industry, if you have a catalyst, you can use it again and again and again and again to speed up your reaction and produce your product. And the good thing is you can use it like a million times and it's not going to get over. Like despite helping you, it stays there with you. So I guess it's the best thing. Okay, H2 is the limiting reactant because use figure 3.2 to describe how the gradient changes as the reaction proceeds. State what this shows about the rate during the reaction. So gradient is decreasing. You can see first it's more steep, then it becomes less steep, and then it becomes less steep, and then it becomes 0. So gradient decreases, and if the gradient decreases, we know the rate decreases. So we know that the gradient decreases, so the rate also decreases, and eventually the gradient is becoming 0. You can see it for yourself. The line becomes flat, that means a 0 gradient, and eventually the gradient becomes 0, so rate becomes 0. Always write more. I don't know why I like this thing, but always write more than what's needed. So rate becomes, teachers will say write precisely, write what's needed, do this, do that. No, write whatever comes inside you, whatever makes you feel that if I write this, I can get it, I can eat it, I can get the mark, right? So if I can get it, why not write? I have the time, I have everything, I have the brains, I have everything. The only problem is I'm not writing what's inside me. That's not fair with you if you don't write what's inside you. the gradient becomes 0, so the rate becomes 0, so the reaction stops. That means it's going to be finish. Hydrocarbon Y contains two carbon-carbon double bond groups. There are no other functional groups present. Y reacts with an excess of H2 to produce C6H14. That means Y initially is going to have 6 carbons, and then when it's going to react with H2, the double bonds are going to be like finish, khalas. Use table 3.1 to calculate the enthalpy change per mole of C6H14 produced in this reaction. First, I have to draw Y. With 2 double bonds, I have to draw 6 carbon atoms. 1 double bond, 2 double bond, and then 6. 1, 2, 3, 4, 5, 6. H, 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 no H here, H, and H. Done? Gonna add H2 to it, and there are gonna be 2 moles of H2 added, because you can see it for yourself. There are 2 double bonds that need to get their treatment done. So it's gonna become a simple 6 carbon atom alkane. 1, 2, 3, 4, 5, 6. H, 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 H. Okay, so this is the reaction that's happening. So you need to calculate all the energy that's going to be given in to break these bonds. So I'm going to start off with my work. I have carbon hydrogen 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 carbon hydrogen bonds. Plus, how many carbon-carbon double bonds? 1, 2. 2 carbon-carbon double bonds. Plus, how many carbon-carbon single bonds? 1, 2, 3. 3 carbon-carbon single bonds. You can see 1, 2, and 3. 3 carbon-carbon single bonds. Plus, 1 hydrogen-hydrogen single bond, another hydrogen-hydrogen single bond. Plus 2 H bonds. Okay, done. Now over here, how many carbon-carbon bonds? 1, 2, 3, 4, 5. Okay, so now this is going to be subtracted. 5 carbon-carbon bonds in the products. How many carbon-hydrogen bonds in the products? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 carbon-hydrogen bonds. Okay. So now from the table, you're going to place the values. 10 times CH bonds. 10 times 410 plus 2 times 610 plus 3 times 350 plus 2 times 436. Okay, this is gonna give me all the energy that's gonna be given into to break the bonds minus all the energy that's gonna be released. 5 times carbon-carbon single, that's 350 plus 14 times CH, 410. And then I'm going to get my answer as enthalpy change. If I put all this stuff into my calculator and calculate it out, what do you guys think I'm going to get? For this part, I'm going to get 7242. And then for this part, minus 7490. I'm going to get negative 248. Done and dusted. Hydrocarbon Y reacts with H2. Okay, no problem. Figure 3.3 shows the distribution of the energies at temperature T. Area A represents the number of molecules with energy greater than the activation energy. Annotate on figure 3.3 to show the effect of adding nickel to Y and H2 at temperature T. So if you add nickel, what's going to happen? The activation energy is going to decrease. So you're going to plot a new line and write EA catalyzed. So that's for your catalyzed reaction. The activation energy is going to move towards your left. It's going to be a little lower. Area B not labeled represents the number of molecules with energy greater than or equal to the activation energy when nickel is added. So this entire area is area B after nickel added, and this area is area A. So area A is less because when you don't have a catalyst, you have less particles that have greater than activation energy, and when you have a catalyst, you have more particles. State the difference in any between areas A and B. Explain the significance of your answer on the rate of hydrogenation of Y. Area B is larger than area A because there's a very important word that explain in terms of significance of the hydrogenation. Give your answer in terms of collision. This is very important. So we have to tell that this is because there are going to be more effective collisions in area B. Why are there going to be more effective collisions? Because the rate is going to increase, because now more particles have energy greater than the activation energy. Now these many particles have been added to the area. So we're going to tell more effective collisions are gonna happen. You don't write gonna, wanna in the paper, but I'm just doing it because obviously this is not gonna go to the the examiner, but just don't use this English in paper. Now we have something interesting that you should pay attention to. Alkene Z contains 2 carbon-carbon double bonds. 2 carbon-carbon double bonds. Z reacts with an excess of hot concentrated acidified KMnO4 to produce only, read it carefully, carbon dioxide, water, CH3, whatever this thing, and this thing. Acha, suggest the structure of Z. Now, I tell you one thing, that कार्बन डाइऑक्साइड सिर्फ तभी बनता है जब आपके पास एक डबल बॉन्डेड कार्बन हो जिसके दोनों साइड्स पे हाइड्रोजन हो. अगर डबल बॉन्डेड कार्बन के दोनों साइड्स पे हाइड्रोजन है तो आपके पास कार्बन डाइऑक्साइड और वाटर बनेगा. इसका मतलब है एक डबल बॉन्डेड कार्बन तो ऐसा है जिसके दोनों साइड्स पे हाइड्रोजन है. डन. अब इस कार्बन के भी मुझे दोनों साइड्स पे कुछ ना कुछ लगाना पड़ेगा, बट आई नो कि इस कार्बन के साइड्स पे हाइड्रोजन, दोनों साइड पे हाइड्रोजन ही है. एक साइड पे कुछ और है, एक साइड पे कुछ और है. अब अगर मैं इधर देखूं, यहाँ पे मुझे नज़र आ रहा है कि मेरे पास एक साइड पे एसिड ग्रुप है COOH और दूसरी साइड पे भी मेरे पास एसिड ग्रुप है. मेरे पास 2 एसिड ग्रुप्स हैं, ठीक है, और सेंटर में एक CH2 है. 2 एसिड ग्रुप्स हैं और सेंटर में एक CH2 है. अच्छा जी, तो अगर मैं ये करने की कोशिश करूँ, अभी मैं सिर्फ हिट एंड ट्रायल कर रही हूँ. 2 एसिड ग्रुप्स हैं, अगर मैं इसको ऐसे करूँ और सेंटर में CH2 है, H, और फिर एक CH है जो कि डबल बॉन्डेड है एक कार्बन के साथ, और प्रॉब्लम है इस कार्बन के ऊपर भी CH3 है, इस कार्बन के नीचे भी CH3 है. सिर्फ अगर ये होगा तो मैं ये वाला कीटोन बना सकती हूँ. नाउ अब आप सोचोगे कि ये क्या हुआ है, ये कैसे बना ये स्ट्रक्चर. ये स्ट्रक्चर ऐसे बना है कि मुझे ये 3 प्रोडक्ट्स चाहिए थे. अब मुझे पता है एक ऐसा क्वेश्चन है जो हर बंदा आराम से नहीं सॉल्व कर सकता, बिकॉज इसमें आपको 2-3 चीज़ें सोचनी है. कार्बन डाइऑक्साइड वाली चीज़ बड़ी आसान थी कि कार्बन लो, उसके ऊपर भी हाइड्रोजन लगा दो, नीचे भी हाइड्रोजन लगा दो. ईजी ना. अब हम आते हैं कार्बोक्सिल वाले पार्ट पे. कार्बोक्सिल वाले पार्ट में थोड़ा सा ट्रिक ये था कि आपको एक साइड पे COH चाहिए था, दूसरी साइड पे भी COH चाहिए था और सेंटर में CH2 चाहिए था. उसके लिए आपको 2 साइड पे कार्बन चाहिए थे जो एक हाइड्रोजन से अटैच्ड हो और एक एल्काइल ग्रुप से. ये कार्बन था, एक हाइड्रोजन से अटैच था, एक एल्काइल ग्रुप से. यहाँ से जब ये बॉन्ड टूटना था तो इसने COH बना लेना था, इस वाले कार्बन ने. अब इस वाले कार्बन को भी मुझे COH बनाना था, तो मैंने साइड पे एक एल्काइल ग्रुप लगाया, ऊपर एक हाइड्रोजन लगा दिया, ठीक है। इसने भी COH बना लिया, मेरा ये वाला प्रोडक्ट बन गया। अब मेरा थर्ड प्रोडक्ट आता है। अब इस डबल बॉन्ड के साथ मुझे अपना थर्ड प्रोडक्ट लगाना था, और थर्ड प्रोडक्ट मुझे ऐसा चाहिए जो मेरा सेंटर में कीटोन बनाए। कीटोन तब बनता है जब आपके पास दो एल्काइल ग्रुप्स डबल बॉन्डेड कार्बन के साथ अटैच्ड हो। मतलब मुझे इस कार्बन के साथ दो एल्काइल ग्रुप्स चाहिए थे, एक एल्काइल ग्रुप ऊपर, एक एल्काइल ग्रुप नीचे। तो मैंने उसके साथ एग्जैक्टली दो एल्काइल ग्रुप्स लगा दिए। अब जब ये बॉन्ड टूटेगा तो यहाँ पे कीटोन बनेगा, बिकॉज मुझे कीटोन चाहिए था। पर ये ना स्ट्रक्चरल फार्मूला है, ना कुछ और है, ना फुली डिस्प्लेड है, तो ये फार्मूला तो मेरा इनकरेक्ट माना जाएगा। इसको मुझे प्रॉपर स्ट्रक्चर की फॉर्म में लिखना है। अगर मैं इसको स्ट्रक्चरल फार्मूला की फॉर्म में लिखूँ तो ये बनता है CH2 डबल बॉन्डेड, अब मैं यहाँ से शुरू कर रही हूँ, ठीक है। डबल बॉन्डेड CH बॉन्डेड टू CH2 CH डबल बॉन्डेड C, और ये दो CH3 लगे हुए हैं साथ, ठीक है, CH3 ये स्ट्रक्चरल फार्मूला है मेरा। और अगर मुझे इसका डिस्प्लेड फार्मूला बनाना है तो मैं अपनी लॉन्गेस्ट कार्बन चेन सेलेक्ट करूँगी। ये मेरी लॉन्गेस्ट कार्बन चेन है जिसमें आ रहे हैं 1 2 3 4 5 6 कार्बन्स, 1 2 3 4 5 6 कार्बन, 6 कार्बन्स हो गए। फर्स्ट सेकंड कार्बन पे एक ब्रांच लगा हुआ है, सेकंड कार्बन पे एक ब्रांच लगा हुआ है, ये हो गया। अब मेरे पास जिस कार्बन पे ब्रांच लगे उसके आगे वाले कार्बन के साथ उसका डबल बॉन्ड है, उसके आगे वाले कार्बन से उसका डबल बॉन्ड है, और लास्ट कार्बन में एक डबल बॉन्ड है यहाँ पे, तो लास्ट कार्बन में एक डबल बॉन्ड है। डन हो गया, सिंपल था, बस थोड़ा सा टेक्निकल था, आपको कुछ एक दो चीज़ें समझनी थी, एंड दैट्स ऑल, दैट्स हाउ यू गोना डू इट। अच्छा, अब प्रोपेनोइक एसिड जो है रिएक्ट्स विद द रिड्यूसिंग एजेंट Q टू प्रोड्यूस प्रोपेन 1-ol, सजेस्ट द फार्मूला ऑफ रिड्यूसिंग एजेंट Q। अब हमारे पास दो रिड्यूसिंग एजेंट्स हैं सिलेबस। द फर्स्ट इज़ NaBH4 एंड द सेकेंड इज़ LiAlH4। अब इन दोनों में से हम कौन सा यूज़ करेंगे ये हम पे डिपेंड करता है, पर अगर किसी ने ये वाला यूज़ किया तो उसको मार्क्स नहीं मिलेंगे, क्योंकि एसिड को जब हमने रिड्यूस करना होता है ना, एल्डिहाइड कीटोन के लिए हम NaBH4 यूज़ कर सकते हैं, बट एसिड पे NaBH4 काम नहीं करता। For acids, we can only use LiAlH4. Just write it down somewhere कि acid is the organic acids, they're only going to be reduced by LiAlH4. Complete the equation to show the reduction of propanoic acid to propan 1-ol. Use H to represent the one atom of hydrogen. Okay. वैसे तो I can do it without even explaining it to you guys, but I'm going to explain. अब देखो हो क्या रहा है, ये आपके पास प्रोपेनोइक एसिड है, इससे आपने बनाना है प्रोपेनॉल। सबसे पहले आप क्या करोगे, आप यहाँ से ये ऑक्सीजन और इसका 1 बॉन्ड निकाल दोगे, ठीक है। प्रोपेनॉल बनाने के लिए यहाँ पे एक हाइड्रोजन लगाओगे, यहाँ पे एक हाइड्रोजन लगाओगे, और जो ये ऑक्सीजन है इसके साथ 2 हाइड्रोजन्स लगा के ये बना लोगे 1 मॉलिक्यूल ऑफ वाटर और 1 मॉलिक्यूल ऑफ प्रोपेनॉल। अगेन आई एम गोना शो यू व्हाट आई डिड। इसको ज़रा गौर से देखें मैंने क्या किया। मैंने डबल बॉन्डेड कार्बन में पहले ये बॉन्ड तोड़ा, उसके बाद मैंने यहाँ पे हाइड्रोजन लगाई, यहाँ पे एक हाइड्रोजन लगा दी, यहाँ पे 2 हाइड्रोजन्स लग गई, उसके बाद मैंने यहाँ पे 2 हाइड्रोजन्स लगा दी, वाटर बन गया और प्रोपन 1-ol बन गया। सो इसका मतलब है हमारे पास 4 हाइड्रोजन्स चाहिए, 2 हाइड्रोजन्स इधर लगेंगी और 2 हाइड्रोजन्स इधर लगेंगी। सो हमारा बनेगा CH3 CH2 CH2OH प्रोपेनॉल प्लस हमारे पास एक वाटर का मॉलिक्यूल बन जाएगा। डन हो गया। Propan 1-ol is converted to compound T in a 3-step synthesis. Step 1 is SOCl2 is added to Propan 1-ol to produce E. जब हम एक अल्कोहल में अल्कोहल में SOCl2 डालते हैं तो हमारे पास क्या बनता है, हमारे पास हैलोजेनो एल्केन बनती है। आपको याद है, हैलोजेनो एल्केन बनेगी। In step 2, E, which is a halogeno alkane, reacts with a suitable reagent to produce butane nitrile. अच्छा, अब मैं आप लोग को समझा रही हूँ हो क्या रहा है। सबसे पहले हमारे पास है एक अल्कोहल, अल्कोहल में हमने डाली SOCl2, हमारे पास बन गई हमारे पास बन गया हेलोजेनो एल्केन। अब हेलोजेनो एल्केन में से हम ब्यूटेन नाइट्राइल कैसे बना सकते हैं? हेलोजेनो एल्केन में डालेंगे KCN अल्कोहलिक और उसको हीट करेंगे तो बन जाएगी ब्यूटेन नाइट्राइल। स्टेप 3 ब्यूटेन नाइट्राइल इज़ हीटेड विद NaOH। अच्छा जी, तो अब हम नाइट्राइल की हाइड्रोलिसिस कर रहे हैं। जब हम उसको NaOH में हीट करेंगे तो अल्कलाइन हाइड्रोलिसिस हो जाएगी ना। अब नाइट्राइल की हो रही है हाइड्रोलिसिस, जिससे वो बन जाएगा ब्यूटेनोइक एसिड। ब्यूटेनोइक एसिड। तो अब ये हो रहा है, पहले एक अल्कोहल एक हैलोजेनो एल्केन में जा रही है, फिर हैलोजेनो एल्केन एक नाइट्राइल में जा रहा है, और फिर नाइट्राइल की हाइड्रोलिसिस होके वो एक एसिड में जा रही है। अब देखते हैं व्हाट द क्वेश्चन इज आस्किंग। नेम द टाइप ऑफ रिएक्शन दैट अकर्स इन स्टेप 1। स्टेप 1 में क्या हो रही है? अल्कोहल हैलोजेनो एल्केन में जा रही है। अल्कोहल का जो OH है वो सब्सटीट्यूट हो रहा है बाय एक एल्कली, सो दैट इज कॉल्ड न्यूक्लियोफिलिक substitution reaction. Identify the reagent and conditions in step 2. स्टेप 2 में क्या हो रही है? हैलोजेनो एल्केन ब्यूटेन नाइट्राइल में जा रही है, तो KCN इन एथेनॉल एंड हीट। KCN इन एथेनॉल एंड हीट करनी है आपको। कंस्ट्रक्ट एन इक्वेशन टू डिस्क्राइब द रिएक्शन ऑफ ब्यूटेन नाइट्राइल विद NaOH इन स्टेप 3। अच्छा जी, अब ये इक्वेशंस बच्चे अक्सर नहीं याद करते और फिर उन्हें लॉस हो जाती है। कंस्ट्रक्ट एन इक्वेशन। ब्यूटेन नाइट्राइल क्या होता है? CH3CH2CH2C ट्रिपल बॉन्ड N, राइट। ये ब्यूटेन नाइट्राइल हो गई। हम चलो बॉन्ड्स नहीं बनाते, हम सिर्फ CN लिख देते हैं। प्लस इसमें डालेगा NaOH एक्वस, और हमारे पास बनेगी ब्यूटेनोइक एसिड। इसमें एक वाटर भी डलेगा। आई फॉरगॉट टू टेल यू, इसमें एक वाटर डलेगा। वैसे तो रिएक्शन में 2 होते हैं, बट जब ये पूरा रिएक्शन कंप्लीट होता है ना, तो एक वाटर दोबारा जनरेट हो जाता है, तो वो फुल इक्वेशन में कट जाता है। तो अभी के लिए आप छोड़ दें, इसमें बस एक वाटर आपने डालनी है। वाटर डालेंगे तो आपकी बनेगी ब्यूटेनोइक एसिड CH3CH2CH2COOH और प्लस अमोनिया गैस NH3। ये जो N है ना, ये अमोनिया गैस बना देगा। 2 हाइड्रोजन इसको यहाँ से मिलेंगे और एक और वाटर का मॉलिक्यूल होएगा, बट एंड पे क्योंकि रीजनरेट हो जाएगा तो कट जाएगा। ये इसकी फुल इक्वेशन है जो आपने याद करनी है। और बिकॉज यहाँ पे हमारे पास एसिड बना है और हमारे पास एक एल्कली है, तो एक आखिरी चीज़ जो आपने इस इक्वेशन में करनी है, इस H की जगह आपने Na लगा देनी है। Type of reaction that occurs in step 3, what we're doing is we're doing hydrolysis, because basically we're just adding water and then we're adding NaOH. That's alkaline hydrolysis. So you can write alkaline. If we add HCl, then we're doing acidic hydrolysis. Compounds A, B and C belong to the alcohol homologous series. Each molecule A, B and C contain 4 saturated carbon atoms. Identify the type of hybridization shown in the saturated carbon atoms. sp3 hybridized. When carbon is saturated, that means it makes 3 single bonds, and when 4 single bonds, and when carbon makes 4 single bonds, it is sp3 hybridized. Identify the gas produced when sodium is added to sample of alcohol. We produce hydrogen gas. Describe the role of sodium when it reacts with alcohol. What happens is that sodium is, what it's going to do is it's going to make H plus ions go into hydrogen gas in which they have a 0 oxidation state. So H plus is being reduced, and what's being reduced is an oxidizing agent. So sodium is a reducing agent here. Okay, so sodium is going to be reducing agent because hydrogen is being reduced. So who's reducing it? Sodium is reducing it, because in alcohol hydrogen has an oxidation state of +1, but in hydrogen gas it has an oxidation state of 0. So that's why it is acting as a reducing agent, and hydrogen ions acting as oxidizing agents. Shows the results of 2 tests on separate samples of A, B and C. For A, Okay, they're all alcohols, I know. Remains orange, heat under. So that means if it remains orange, it doesn't get oxidized. Then that means A is a tertiary alcohol, because I know that my tertiary alcohols are not oxidized. Warm with alkaline I2, no change. That means it does not has this group attached to it. It does not has, and obviously it cannot have, because इसके साथ ये हाइड्रोजन नहीं हो सकती, बिकॉज इसको एक टेरिशरी अल्कोहल होना है, और टेरिशरी अल्कोहल आपको कभी आइडोफॉर्म वाला टेस्ट नहीं दे सकता, क्योंकि आइडोफॉर्म के टेस्ट के लिए आपको अल्कोहल की OH वाली कार्बन के साथ ऊपर हाइड्रोजन चाहिए होती है. ऑरेंज टू ग्रीन, नो विजिबल चेंज. इसका मतलब है ये हमारे पास कोई प्राइमरी अल्कोहल हो सकती है. प्राइमरी अल्कोहल क्यों हो सकती है मैं आपको बताती हूँ. क्योंकि ऑरेंज टू ग्रीन हो रही है मतलब ऑक्सीडाइज हो रही है, मतलब टेरिशरी नहीं है. बट अगर ये सेकेंडरी अल्कोहल होती तो हमें आइडोफॉर्म टेस्ट देती, बिकॉज सेकेंडरी अल्कोहल्स तो आइडोफॉर्म टेस्ट देती हैं. तो ये कोई प्राइमरी हो सकती है अभी मैं कंफर्म नहीं हूँ. और ये येलो प्रेसिपिटेट भी दे रही है, ऑक्सीडाइज भी हो रही है, तो ये मुझे लगता है हमारे पास होगी कोई सेकेंडरी अल्कोहल. डिड्यूस द स्ट्रक्चर ऑफ ए. बहुत आसान है, क्योंकि हमें पता है कि हमारे पास 4 कार्बन एटम्स हैं. तो एक C बनाओ, OH बनाओ, एक साइड पे CH3 बनाओ, ऊपर CH3 बनाओ, साइड पे CH3 बनाओ. अगर इसको ज़रा आपने उस तरह बनाना है, स्ट्रक्चरल फार्मूला में लिखना है, तो लिखो CH3 3COH. ये इसका स्ट्रक्चर बन गया. रिड्यूस द पॉसिबल नेम फॉर बी. बी हमारे पास एक प्राइमरी अल्कोहल है, तो मैं आपको बता रही हूँ ये होएगी ब्यूटेन 1 ऑल. ठीक है, इसको अगर इसने ब्यूटेन 2 ऑल लिखा तो वो गलत होएगी, बिकॉज ब्यूटेन 2 ऑल आपको आइडोफॉर्म टेस्ट देगी. आप चेक कर लें ब्यूटेन 2 ऑल में ये वाला ग्रुप होएगा. रिड्यूस द आइडेंटिटी ऑफ C. अब ये होएगी ब्यूटेन 2 ऑल. मैंने आपको कहा था ना ये सेकेंडरी अल्कोहल होएगी, तो ये होएगी ब्यूटेन 2 ऑल. जिसकी बात नहीं समझ आई वो ये सोच ले कि जो ब्यूटेन 1 ऑल है ना, उसने आपको आइडोफॉर्म टेस्ट नहीं देना. ठीक है, उसने आपको आइडोफॉर्म टेस्ट नहीं देना, ब्यूटेन 2 ऑल ने देना है. तो ये ऑक्सीडाइज दोनों होंगी, तो दोनों ऑक्सीडाइज हो रही हैं, बट ब्यूटेन 1 ऑल जो है वो आइडोफॉर्म टेस्ट नहीं दे रही, ब्यूटेन 2 ऑल दे रही है. तो बस ये बात है. द स्ट्रक्चर ऑफ वाइटामिन C शोन रिड्यूस द एम्पिरिकल फार्मूला वाइटामिन C. चलें कार्बन एटम्स काउंट करें. 1 2 3 4 5 6 C6. हाइड्रोजन्स का ऑक्सीजन काउंट करें. 1 2 3 4 5 6 O6. अब हाइड्रोजन्स काउंट करें. हाइड्रोजन्स यहाँ पे होंगी दो हाइड्रोजन इधर होएंगी, एक इधर होएगी, एक इधर होएगी. 1 2 3 4 डन. 1 2 3 4 1 2 3 4 डन. सो कितनी होएंगी? H होएंगी 1 2 3 4 5 6 7 8. H होएंगी 8 आपके पास, H8. तो इसको अगर आप कट करें 2 3 टाइम्स, 2 4 टाइम्स, 2 3 टाइम्स, एम्पिरिकल फार्मूला होएगा C3H4O3. द मास ऑफ वाइटामिन C अब जो है वो ये है. अच्छा, वाइटामिन C का जो मास है वो 150 ग्राम लेमन्स में ये है. जो सारा वाइटामिन C है 150 ग्राम लेमन्स में वो एक्सट्रैक्ट हुए, डिज़ोल्व हुए वाटर में टू मेक इतना L. 25 cm³ आपने L लिया, उसको टाइट्रेट किया इतने मोल पर DM³ आयोडीन के साथ. आपका इतना वॉल्यूम यूज़ हुआ आयोडीन का इतने सैम्पल ऑफ L के साथ. अब वो कह रहे हैं अमाउंट कैलकुलेट करते हैं अपने आयोडीन की. अच्छा, अब आपको आयोडीन की वॉल्यूम दी हुई है और आयोडीन की कॉन्सेंट्रेशन दी हुई है. तो अगर हमने मोल्स कैलकुलेट करने हैं तो वो होंगे हमारा वॉल्यूम जो कि है 36.65 cm³ में. हम इसको DM³ के लिए 1000 से डिवाइड कर देंगे, मल्टीप्लाइड बाय द कॉन्सेंट्रेशन जो कि 5.00 इंटू 10⁻⁻³ फिर आप इसे मल्टीप्लाई करेंगे तो आपके पास आएगा 1.833 इंटू 10⁻⁻⁴. आ गई आयोडीन की अमाउंट 1.83 इंटू 10⁻⁴. वैसे सब कुछ आपको ये 3SF है, ये 4SF है, ये 3SF है, बस यहाँ जो दिल करते लिखते हैं, छोड़े. Use your answer to BI to calculate the percentage by mass of vitamin C present in 150 gram of lemon. अच्छा जी भाई, 1 मोल आयोडीन के साथ 1 मोल विटामिन सी रिएक्ट करती है, तो इसका मतलब है विटामिन सी के मोल्स भी इतने ही हैं. विटामिन सी के मोल्स पता चल गए. जो विटामिन सी के मोल्स आपको पता चल गए हैं, तो अब विटामिन सी की वो क्या थी, वॉल्यूम कितनी थी. 25 में आपके पास इतने मोल्स आ रहे थे ना, 25 में इतने मोल्स आ रहे थे, तो खुद ही कैलकुलेट कर लें. 100 टोटल सोल्यूशन था, 100 में कितने मोल्स आएंगे. अगर 25 में आपके पास 1.833 इंटू 10⁻⁻⁴ आ रहे थे, तो 100 में आपके पास x मोल्स आएंगे. 100 में जब आप x की वैल्यू निकालेंगे, जो भी वैल्यू आपके पास आएगी, 100 इंटू 1.833 इंटू 10⁻⁻⁴ डिवाइडेड बाई 25, ये आपके पास मोल्स आ गए. कैलकुलेट कर लेना, ठीक है. मोल्स आ गए. अब मोल्स को जब आप MR से मल्टीप्लाई करेंगे विटामिन सी के, जो कि 176, आपको 100 में मोल्स चाहिए ना. आप 25 वाले को MR से मल्टीप्लाई करते हैं, क्योंकि जो पूरा लेमन है ना 150 ग्राम, उसका 100 का सोल्यूशन बना है. तो ये आपके मोल्स आ गए. अब आप मोल्स को अपने मल्टीप्लाई करते हैं इसके MR से, जो कि 176, तो आपके पास आ जाएगा मास ऑफ विटामिन सी. ठीक है. जब आपके पास मास ऑफ विटामिन सी आ जाएगा, तो आपने अपने मास को ऊपर रखना है, नीचे 150 को रखना है. ये ऊपर इस पार्ट की कैलकुलेशन आएगी, मल्टीप्लाइड बाय 100 करना है, तो आपके पास आ जाएगा जो आंसर आपके पास आएगा, बस उसी को ही ले लेना. 0.086% आंसर आ जाएगा, और सही आंसर होएगा. The progress of the reaction of vitamin C with iodine to produce M is monitored using infrared spectroscopy. Table 5.1 indicates the presence of some absorptions of the infrared spectrum of vitamin C. Complete table 5.1 to predict which of these absorptions, if any, are present in infrared spectrum of M. I2 to produce M. अब M क्या है हमारे पास, M है ये वाली चीज़. तो M में हमारे पास ये कीटोन ग्रुप्स आ रहे हैं, ये कोई एस्टर टाइप ग्रुप आ रहा है, OH वाले ग्रुप्स आ रहे हैं, और डबल बॉन्ड नहीं है. यहाँ पे डबल बॉन्ड थी, यहाँ पे डबल बॉन्ड नहीं है. चलो अब देखते हैं वो हमसे क्या कह रहे हैं. कह रहे हैं M में 1500 से 1680, मतलब कार्बन डबल बॉन्ड कार्बन होएगी, नहीं होएगी. क्यों नहीं होएगी, बिकॉज डबल बॉन्ड मैंने आपको बताया कि टूट गई है. अगला वो कह रहे हैं M में 2850 से 2950. एल्कीन होएगी, एल्कीन तो ऑब्वियसली होगी, वो तो हर कॉम्पाउंड में होएगी ऑर्गेनिक, CH वाला बॉन्ड. अगला वो कह रहे हैं 3200 से 3650 पे होएगी, हाइड्रोक्सिल होएगी. हाँ, M में हाइड्रोक्सिल होएगी, बिकॉज देखें उसके OH अभी भी इंटैक्ट हैं, सो हाइड्रोक्सिल होएगी. तो आसान था, ख़त्म पेपर.